On to our fourth objective, which is to describe the process of neural integration and the role of the axon hillock. Okay, how does the axon hillock come into play? Some of the terms and concepts we're going to describe are summation. We've looked at summation a bit earlier. Frequency coding, and frequency coding just means that we're using the frequency of action potentials to code for different types of signals. Okay, a fast signal, a slow signal, strong signal, a weak signal is all coded in the number of action potentials. We're also going to look at divergence and convergence, which are two mechanisms of summation. And then we're going to talk about the axon hillock and the location of determining the threshold value. So an action potential is triggered as long as the membrane potential gets to threshold, and this has to happen at the axon hillock. If we have enough graded potentials to depolarize the axon hillock to -55, then we fire an action potential. If the graded potentials are below threshold when they are at a sum at the axon hillock, then we do not have an action potential. Now, when you look at divergence and convergence, these are two mechanisms of neurons communicating to each other. So here's a presynaptic neuron. Here are several postsynaptic, excuse me. I apologize, guys. I may be coming down with a cold or something. All right, so a presynaptic neuron synapsing onto a few postsynaptic neurons. And remember, we talked about the axodendritic and axosomatic types of synapses being the most common. And so this is an example of divergence. So we've been looking at the neuron to neuron synapse, and we've been talking about this as kind of this one-to-one interaction. But in reality, a single neuron synapses with many, many other neurons. This is how we have this, this complex network of billions of neurons sending many types of signals from one to the other in different directions throughout the nervous system, right? So they're going to be ascending, descending, afferent, efferent. So there's a lot of different complex network happening. So this neuron is actually diverging its signal. So this signal is going to get split off because we have many different axon terminals synapsing onto each of these postsynaptic somas. Now in convergence, this is the opposite. And this is also the way that the nervous system is sort of orchestrated. So many different axon terminals are converging onto a single cell body or soma. And so that signal is going to get sort of amplified on the soma of this neuron. All right. So these are coming from different presynaptic neurons. We also want to make note of that. Many different presynaptic neurons are synapsing here, and then a single neuron can synapse onto many different somas as well. Now, just recalling summation, we did talk about summation earlier, but just to kind of get into some more details, we can add or sum or total all of the different types of graded potentials that are arriving on the cell body. So if it's an EPSP and that's an IPSP coming in, we're going to add everything together. If they are close enough in space, right? If they're at the same spot on the neuron, okay. Sorry, I'm trying to find this. Okay, I'm sorry, I thought this had, oh, it does. Okay, it's at the bottom here. So the two types of summation, temporal summation and spatial summation, right? So in the panel at the top here, here's temporal summation. These signals are coming in close enough in time. They're in the exact same time frame. So what we see is that the synapses are going to be bringing in either IPSPs or EPSPs. And because they're happening so close together, we can simply add them together. So in temporal summation, they're at the same spot, and in spatial summation, they're at the same time, okay? So looking at, well, I think I said that wrong, sorry. So temporal summation, they're at the same spot, the same synapse. Spatial summation, they're at the same time. So we're looking at adding them together, and notice how, because these are looking at the synapse happening at A, they're coming in close enough in time, but the same exact spot on the neuron. And we sum them. Now we have enough of a graded potential to get us to -55. And so we fire an action potential. And then for spatial summation, they're coming in close enough in terms of their spatial location, right, at the same time. And so now we have two smaller graded potentials and an IPSP, which is our hyperpolarizing event, and we add those together, and that is enough to get us to threshold, so we do eventually fire an action potential. All right, so temporal is one synapse through time, and spatial is several different synapses at the exact same time. All right, one synapse close enough in time versus the same or several synapses at the exact same time. So both of those can be ways that just helps us to get closer to -55 by looking at many different synapses on the soma. Now, frequency coding, we said, is just kind of coding depending on the type of signal, the strength of the signal. And so the degree of depolarization at the axon hillock is signaled by the frequency of action potentials that are arriving. So we're summing, basically, summation is affecting the depolarization. So the ability to add these graded potentials together actually can get us closer to depolarization. And so this is going to influence how fast those action potentials are coming in, right? Because we can start adding them together. If they're close enough in space or close enough in time, we can start combining them. So summation is one of the mechanisms of bringing about the frequency coding of action potentials. Now, if more action potentials come in, more neurotransmitter is going to be released. If action potentials are coming in at a faster rate, this is going to help get us closer to either an IPSP or an EPSP on the subsequent neuron, so on the postsynaptic side of the cleft. And that can help to get us to either excitatory change or inhibitory change as a result of more neurotransmitter. All right, so this is how we decipher different types of signals. It's really important to think about. I kind of like to zoom out and look at a more practical example of this, especially since we'll get to this when we look at muscle. But if you want to have more strength, more contraction, more of any type of signal, this is even how our sensory systems work. If we listen to a louder sound, right, the neurons in our brain, the neurons in the vestibular cochlear neuron, for example, in the ear, will send faster action potentials to send the signal of a louder sound, right? If we're listening to a softer sound or a more quiet sound, that's going to result in a slower frequency of action potentials. And so throughout our body, the different types of signals are sort of transmitted by way of manipulating the frequency of the action potential, which result in the amount of neurotransmitter released. Now, we also have presynaptic modulation. So this is the way that we regulate synapses on the presynaptic side. And this is specifically using the axo-axonic type of synapse. And we looked at this earlier, and I mentioned that you could kind of make a note at this type of synapse. Although it's rare, it has a specific function in terms of modulating the synapse. So there can be presynaptic facilitation or presynaptic inhibition based upon this axo-axonic synapse. And what's happening is the modulating neuron is synapsing onto the axon terminal. So it's an axon to the axon type of synapse. Now, what this does is this can either encourage or inhibit the amount of neurotransmitter released from this presynaptic neuron, which is again going to very much affect the signal being sent from this presynaptic neuron to the adjacent cell body, right? The adjacent soma. So that will either strengthen the signal, make it more sort of augmented, or that can dampen the signal depending on how we modulate the amount of neurotransmitter being released. All right, let's look at two examples of this. So presynaptic facilitation, and facilitation means that we're encouraging this release, right? We're gonna make it a stronger signal, if you will. So here is our neuron. Here's the soma, neuron X in question. D is one synapse, right? C is another type of synapse happening. E is the modulating neuron. Now, I want to make it clear that the modulating neuron does not influence directly the membrane potential. It is not synapsing onto the cell body here. So it doesn't really on its own change the membrane potential. All that it does is it encourages more neurotransmitter to be released. Okay, so here is the action potential from neuron C. And then here is how the modulating neuron, which is E, augments or facilitates or stimulates more of that neurotransmitter to be released. So what we end up seeing is that here is what the membrane potential looks like with just C alone. Here is the membrane potential with just D on its own. Notice that E alone has zero membrane potential change. This is not directly stimulating or having an effect on the membrane potential on neuron X. E has zero direct influence on the membrane potential of the neuron X. Instead, when we look at C and E together, C is going to release more neurotransmitter, which is going to result in more of a greater potential that actually gets to threshold because of the effect of E. Okay, so the modulating neuron just makes it more likely, more favorable, more easy to get to threshold on the opposite, on the cell body or soma of the postsynaptic nerve. For presynaptic inhibition, this is the opposite. So here we have neuron G, here we have neuron F, and neuron H in this case is the modulating neuron. And in this example, it is inhibiting the neurotransmitter release. So looking at the membrane potential change, here is F on its own, has a small membrane potential change. Here is G on its own. Again, a small depolarization. Here is H on its own, zero change, right? Zero direct effect on the membrane potential. And then here is F plus H. So now F, the signal that's released by F is now dampened or decreased. All right, because F is now releasing less neurotransmitter, and that's going to bring about a weaker signal on the postsynaptic neuron. If you look at F plus G, which are the two activated neurons here, then that would in fact bring us to threshold. So the modulating neuron in presynaptic inhibition dampens the signal, dampens the amount of neurotransmitter, makes it harder to result in a stronger, greater potential on the postsynaptic neuron. All right, so just to compare here again, so the axoaxonic type of synapse either excites or inhibits another existing synapse. And this is selective in that it really depends on the type of neurotransmitter being released and the type of synapse that it is modulating as well. For axodendritic and axosomatic, this can be either excitatory postsynaptic potentials or inhibitory postsynaptic potentials, and these are non-selective. As long as that neurotransmitter crosses the junction, it's always going to open up its receptor and it's going to bring, or close, right? Open or close its corresponding receptor, and it's going to bring about that type of change on the neuron. So it's not really selective. It's really the neurotransmitter that's determining the type of response on the adjacent neuron. But I also want to point out that these types of synapses are going to result in postsynaptic potentials, right? The axoaxonic is not really directly resulting in a potential or a graded change. It's not going to be changing the membrane potential. All it does is it encourages or inhibits the amount of neurotransmitter released. Okay, so just to kind of really summarize what we've been saying so far and kind of put sort of a big picture summary here, we have been talking about the graded potentials and how they are summed and how they result in action potentials. So when we kind of zoom out and look at the neuron more holistically, we can see the location where we have the graded potentials arriving. So remember, the graded potentials here are arriving as a result of the synaptic transmission, the details that we looked at with the calcium channels opening up, right, which is happening here on the axon terminal, the release of a neurotransmitter, and then the neurotransmitter crossing the cleft here. So although we can't really see it in this kind of more zoomed out view, there's a cleft where the neurotransmitter crosses and binds onto receptors on the cell body of the postsynaptic neuron. Now, all of this needs to be integrated. This is called neural integration. And this kind of happens at the axon hillock. So the axon hillock is where we are assessing all of the information that's coming in on the cell body, whether it's EPSP, IPSP, presynaptic facilitation, presynaptic inhibition, all of that is being assessed and calculated, summation, convergence, divergence, all of that is taken into account. And if we are netting at -55, all of those signals in account, then we fire an action potential. It moves down the axon of our postsynaptic neuron, and then we start all over again, right? We have neurotransmitter released, and we have this happen all over again. And so this is how our neurons speak to each other. This is how we have all of the different types of signals throughout our sensory system are perceived by way of neurons using this neurotransmitter to send signals back and forth to one another. Okay, so really important to kind of know the intimate sort of, intricate details, but also zoom out and put this into perspective as far as how it's practically applied in the body, right?